All right, so we've looked recently at solubility product constant, right? And we've talked about how a substance dissolves, and if the solubility product constant is high, there's lots of ions, right? The dissolved ions in solution. And it's the same as a equilibrium constant that we looked at before. We're talking about acids and bases, and I want to talk to you today about a special constant called the ionization constant for acids and for bases, but we're going to stress the acids. Just like Keq and Ksp tell us, how much something dissolves, or how much product is formed in a reversible situation as far as Keq goes. Ka tells us how strong an acid is by giving a number value to the ability for an acid to release its hydrogen ions. So if we go through these notes here, based on the equilibrium constant, and that's where it all starts, it's kind of where the Ksp starts as well. The Ka, and this is the new symbol for the constant, Ka, it's the ionization constant for an acid. Now, what is ionization? Ionization is when something ionizes or turns into ions. And so for acids, you know that acids, like let's say HCl is a very common one, right? It's going to dissociate into H plus Cl minus. Or as we've learned, really what happens is in water, oops. Oh, is it not working? There you go, you can see that now. Thank you. For HCl, really it combines with water and produces the hydronium ion, right? So HCl, hydrochloric acid, is very, very strong. And it has an extremely high Ka value. So strong acids have Ka values that are extremely high. And because these acids completely ionize, like really there's no comparison with the amount of ions in solution versus the acid that remains. So oftentimes there's no number given for really, really, really strong acids like HCl. Because this just goes one way, it completely ionizes because it's so strong. That's what makes it strong. Does it completely ionize or just partially ionize? And so for really strong acids, you'll see that there's no number given. It just say Ka is very high, like extremely high. Okay? So the higher the Ka, the stronger the acid. So the constant indicates how strong an acid is by giving this a number value, as I mentioned before, for the ability for an acid to release hydrogen ions in solution. So if an acid has a high Ka value, that means it's a strong acid, and it also means that it produces a lot of hydronium ions in solution. That is very, very large. Now, a weak acid, okay, so if I give you an example of a weak acid, actually I'll just kind of scroll down here, and we'll just finish these notes off here before I do this. So if strong acids, they completely ionize, so the Ka value is just very high.
Mr. Martin, please call 205.
So this value is useful when we're talking about weak acids. And I'll get you to turn to page 860, kind of when you have this stuff jotted down here. Page 860, and you'll see some weak acids and their Ka values. Okay, so this chart's not exactly like yours on page 880, but this is an example of a Ka value chart. So let's take a look here. Hydrochloric acid, that's the one we just talked about, right? It completely dissociates. It's a very, very strong acid. And so you see the Ka here, and don't worry about the per moles per liter, but the Ka value, the constant is just very large, okay? Because really the ions are so large in solution compared to a very small amount of the original HCl that remains, that number, if you think about the Keq or the Ksp expression, right? It's the ions on top, the product of the ions on top, and it's the concentration of what started off. That's on the bottom. So when that's really close to zero, you're dividing by a number that's super close to zero, then that number becomes super large. But if we move down the list here, sulfuric's pretty strong. Nitric is really strong too. But if you look down here, let's go to acetic acid. Okay, so acetic acid right here. Does anyone know where the acetic acid is found? Vinegar. Yes, that's right. It's commonly found in vinegar. That's usually the first one that people mention. But anyways, the Ka value, you see this, is 1.8 times 10 to the negative 5. So acetic acid, 1.8 times 10 to the negative 5. And what this means is that here's the acetic acid molecule here, and this H that's going to get kicked off, that's going to ionize, it's going to get released into solution, this concentration is pretty low, actually. This doesn't completely ionize, it only partially ionizes, and you have a constant that's kind of on the low side. Anything that's below 10 to the negative 4 is extremely, extremely weak. These are just anything above negative 4, up to 1 is kind of in the middle area. But you can kind of see that as we move down the list here, an ammonium ion right here, NH4 plus, okay, it's not a very strong acid at all. It's got a very low Ka. Okay, so that just basically means that the concentration of this ion is not going to be very high. Where Ka is large, the concentration of hydronium ion is super large. Okay, does that make sense? All right, so that's what Ka means. Okay, let's continue on with the notes here. The Ka value, as I mentioned, and I've talked about this already, but just get it down in your notes. The Ka value is used in a similar way to the Ksp values and also to the Keq in determining concentrations of substances when a weak acid or base ionizes in solution. So it's very similar to the Ksp. The Ksp tells how well something will dissolve, right? As I mentioned at the beginning of the class. And Ka tells how well an acid dissolves or ionizes. That is, spits out its hydrogen ions. Okay, so just before you take this note down here, okay, just before you take that, don't write this down yet. I want to just jump down and just show you some formulas and some examples. Okay. Okay, so what we're going to do is we're going to write down 2 examples of each here, and I want you to see how the Keq, the Ksp, and the Ka look similar and are related, and what the major difference is with the Ka. So I asked you guys to come up with a Keq expression, just any one. Did you find one in the textbook there? Yeah? Okay, what do you got? Okay, so go ahead and read it out to me. What does it say? 565? Okay, everyone can go to 565. Keep your... okay, no, okay, but what I want is the chemical equation. Okay, and then the Keq. So from the page before, so we've got this one, N2, you want to do this one, plus 3H2, and then of course it's a reversible reaction, and on the other side here we've got 2NH3. Okay, so in the Keq, in writing the Keq expression, right, we have the concentration of the products, and there's one here, so concentration, that's square brackets, NH3, and what do I do with this 2 here, you remember? Do I times 2, or what do I do? What does this 2 do? Exponent, right? In the Keq, the coefficients are exponents, divided by, and these are all gas, so that's good, concentration of N2 times concentration of H2 to the power of 3. Alright? So that's an example of a Keq equation and expression. Okay? And remember, it's a chemical reaction, so these 2 are reacting, and they're forming this product, but that product is also reacting in a sense. In this case, it's breaking down to form the reactants again, right? So it's going back and forth. The value of the Keq, if it's high, what does that tell us again? Lots of product, very good. If it's low, lots of reactant at equilibrium. Okay, very good. Okay, the Ksp group, Where did you guys find a KSP expression and and the equation too? I want to write the equation now too. So, did you guys find one? All right. So page 603, we've got this. We've got AgBr, solid, and it is dissolving, and of course reappearing, right? Dissolving into its ions. So it's Ag plus Br minus. Okay. So this is aqueous ions, and that's from this sort of equation, something that's a solid that's just dissolving, gives us the KSP, right? It kind of comes from the Keq style of expression, but because the AgBr here, silver bromide, is a solid, remember that concentration really doesn't fluctuate. It's just the amount that starts to go away. So we wouldn't include this in the KSP. So the KSP expression then is what? Yes, concentration of Ag plus times the concentration of Br minus. Okay, so there's no denominator in a KSP. But again, the value of the KSP, if it's really high, that means that we have lots of ions in solution, and therefore a high KSP means this is very what? This solid is very soluble. Yeah, soluble is what I'm looking for. Yeah, it's very soluble. Okay, so this is a really important review for you guys. You should this should be ringing some bells here, anyways. So the Ka is very similar to both of these two. All right. So if we look at HCl and plus H2O, let's just involve that H2O in there. And we can write this as a reversible reaction, okay, because there will be some HCl left, but not much because it's super strong, right? But this is sort of what happens. Now, water is just liquid water, right? So its concentration doesn't change. So again, stemming from the Keq, we write it exactly the same as a Keq, just like we did to the KSP. But just like this doesn't change, this is not going to change. So Ka really is a special equilibrium constant where you don't include the water. All right? And Ka then looks like this.
So what's the small limitation?
Liquid. That's L for liquid. Okay? So, anyways, you don't have to put any, like these are aqueous, but don't worry about states. But the Ka is, again, very similar, so it's the concentration of H3O plus times the concentration of Cl minus here, and divided by the concentration of the original acid HCl. All right. Now, again, for HCl, Ka is very large because this ion concentration and this ion concentration is super large because this breaks down almost completely. This is super small. And so when you have two large numbers multiplied, it gives a super large number. When you divide it by a number that's really close to 0, that gives you an even larger number. So that's why Ka is super large here. But if we have a weak acid, this Ka then comes into play, and we actually have to use this. We can use this number, you see, in this mathematical equation now to solve for any one of these other things. And that's where we're gonna go now. Okay. So let's do an example here using the Ka, and I'm going to come back to that special note at the end. But let's do an example. All right. Okay. There's not many examples in your textbook, really. So let's take a look again now at this chart. Okay, and let's do an example where we're going to use, well, let's do the acetic acid. Okay, so the acetic acid. All right, and we're going to start off with, like 0.5 moles per liter of acetic acid. All right. Okay, so here's our example where we're going to use Ka to solve the problem here. Okay, listen. So we've got 0.5 moles per liter of acetic acid, and I'm trying to find out what the hydrogen ion concentration or hydronium ion concentration is. Okay, what is this? And we're given here 0.5 moles per liter. Capital M, remember, is moles per liter. If you want to just say moles, you have to write MOL. All right, again, from the labs, and a lot of you mix that up. Now, this volume here, really in this question, you don't need to use that volume because if I gave you moles, you'd have to use this volume to find concentration. If I asked for grams or something like that, molecules, you'd have to maybe use that. But you don't have to use it for this question, but this would be an example of a question that you might get. So for this one, because you don't need to transform this number into moles per liter, you don't have to worry about the volume. Okay? So that's something that in some questions there will be some information that you don't need. But let me just explain here kind of how we need to use this. So the Ka, okay, the Ka expression, let's write that out first. So the Ka is going to be the concentration of H3O plus times the concentration of CH3COO minus all over the concentration of the original acetic acid. Now, is this balanced? Okay, it looks balanced, so these are all ones here. Okay, so we don't need to add any exponents there, just exponents of 1. All right, so let's take a look at what we're given here. The original concentration is 0.5 molars. So we don't have to, again, we don't have to use the volume to convert to moles per liter. So we can use this number. Now, where does this number go in the Ka? Where do I put it? Well, concentration of acetic acid is down here. See that? So in my equation, I'm going to put 0.5 molar down here. And just because we're just going to do the math, you can drop the units. Just put 0.5 if you want. Ka is given, okay, over here. So we're going to put the Ka number here, where the Ka is in the expression. Now this is unknown. So how do you guys remember kind of what you would do here in the KSP or the KEQ? How do we solve for this value right here? How do I solve for this value? What do I have to do in this equation here? What do I have to kind of put in here? Okay, yeah, H3O plus is unknown, right? It's unknown. Yeah, that's right, because this is X, unknown, and because when this dissolves, it's going to be a 1-to-1 ratio, right? So this is going to be X2. However much of this hydronium ion is produced, it's going to be the exact same. Boys, be listening, please. Okay. It's going to be the exact same of this ion here, okay? The acetate ion. So this is going to be X, this is going to be X. Got it? So this is very similar to KEQ, right? It's really used almost exactly the same way. So you solve for X, and I'll just give you a second to do that. Go ahead and solve for X here, so we get the same value. Okay, did you get something like this? Does that agree with what you guys got? Let's see if we did that right. So we've got 1.8 times 10 to the negative 5. Take the square root of that. You should get 0.00424264 equals, this was x squared. Okay. Now, what's missing here? What's missing here? Okay, so what's missing here? What's different from yours? Because there's a mistake in here. There's an error in here. I want you to pick it up. What happened? Did you guys change your answers to this already? Okay, don't change it yet. You probably got the right answer. Tricked you. Okay, so because this happens a lot. This mistake happens a lot. So what should I have done here in this step right here? Multiply the denominator?
Multiply by the denominator.
Okay, so When I took the square root of both sides, you see how I took x squared? I took the square root of x squared, but I did not take the square root of 0.5. Okay, so you got to make sure you do that. All right. So, way it should have looked. Okay, I'll go back here. Sometimes you might want to do this first. You might want to actually do this. So I'll just erase all this here now. You might want to do the 0.5 first and multiply both sides by 0.5 first. How many of you did that? Okay, about half of you did that. That's great. If you don't do that, then you just have to write x over the square root of 0.5 and then multiply that afterwards. But it would be a better idea to multiply the 0.5 first. Okay? So we've got 1.8 times 10 to the power of negative 5 times 0.5. And that's 9 times 10 to the negative 6, right? Okay, 9.0 times 10 to the negative 6 equals x squared. Now you take the square root, and then you don't have to worry about this denominator here. Okay, how many of you did this? Looking just like that? Yeah? So you get an x value of 0.003. How's that look? Yes? What's the unit here on 0.003? What is it? Yes, molar. Moles per liter. Okay? So the acetate ion and hydronium ion, the concentration would be 0.003. So for your final answer, you can write that right here like this. 0.003 molar. All right? All right, so I want to talk about this kind of one major note here in determining, when working with Ka and or Kb, we're going to just focus on Ka for now, but there's one major note, and you need to jot this down, okay? Because acids, okay, may be so weak that they don't release many hydrogen ions at all in solution. And we are talking, like HCl is super strong, but if you have like ammonium ion, okay, the number of hydrogen ions that are in that solution with ammonium is super, super small compared to the original acid concentration. So what I'm saying is that it does not ionize, like hardly at all. So we can simplify our calculations a little bit when acids are extremely weak. So what I want you to know here is, because these acids are weak, the difference between the original acid concentration and the final acid concentration is often next to nothing. Okay? With weak acids, that have Ka values of 10 to the negative 4 or less, this difference can be ignored. And I'm going to do an example for you here in the last 5-6 minutes of class. So, once again, I'll go back to that other page. So when we have Ka values for acids that are less than times 10 to the negative 4, the difference between the original acid concentration and the final acid concentration basically can be ignored, and I'll do an example there. I'll show you. What this does is it makes the math a bit easier, and it doesn't really sacrifice any accuracy. All right, so this is what I mean. Let's go back to this example, guys. Do you see? Now, another thing that we did here, okay? What we ignored. This is the special note that I'm saying. Remember how this is less than negative 4 here? You see that? This is actually less than negative 4. So when this Ka value, listen carefully, is smaller than 10 to the negative 4, like this one is, this is how you do the question. Just like this. But really, if we go back here, look at what we did that's really not quite 100% accurate with the situation. So look at this. This is 0.5 molar, but at equilibrium, right, or in solution, is this actually still 0.5 molar? Think about your ice charts. If this breaks down into this and this, do you see how Actually, this is a little bit less than 0.5 molar because it starts off with a certain amount and then it actually breaks apart into the ions. So in this question, to do this question exactly precisely, what we would have had to do is do this. This original concentration would actually go down by what? X. I heard somebody say it. Because at equilibrium, this is 0.5 minus X. Now, keep this number in mind. I'm going to leave that up there. Okay? But I'm going to let's say that we do this and we actually include this, and we're going to see the difference between the actual answers. And actually, it's going to take a little bit more math. You'll see how it's a little bit tougher. So, if we now multiply both sides by this, so let's do this real quick. All right, so we have, what was that? 9 times 10 to the negative 6 minus 1.8 times 10 to the negative 5 x equals x squared. Now, we can't simply take the square root of both sides. Now we have to do the quadratic formula because it's a quadratic equation. So actually we have 0 equals x squared. And you are going to have to do this type of problem for any Ka values above 10 to the negative 4. So that's why we should practice this. So this is going to be plus 1.8 times 10 to the negative 5x minus 9 times 10 to the negative 6. You put that into your quadratic formula. X equals negative b plus or minus root b squared minus 4ac all over 2a. Very good. You guys know that song. That's awesome. Wonder how you know that. Okay? So what this is negative b is negative 1.8 times 10 to the negative 5 plus or minus, I know, look at how great this is going to be. 1.8 times 10 to the negative 5 squared minus 4c, blah, 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 all over 2 times 1. 2a, right. Okay, so do this real quick on your calculator. Okay, so the point here is that you see when we do all this right here, okay, it comes out to the exact same number here, and so going through all of this math, because that x is so small, right? It basically it's the same as the original concentration. So remember, when Ka values are less than times 10 to the negative 4, you don't have to do this sort of math to kind of finish the question. All right, so write this down before you go. Number 28, page 592. Number 28, page 592. Once you've got that down, that is due tomorrow. Finish all those other questions as well. You may be dismissed. Okay, so just to conclude this question, just another further comment on this question here. It's plus or minus, so when we add this and divide, we get on the calculator what appears to be the exact same number that what we started with. What that means is that when we do the subtraction, okay, so for the other option is 0. What does that tell us? Well, that tells us that x is extremely small. It's virtually 0. It's one of these two answers. It's not the first one. It's actually calculated to be this. Therefore, x is said to be really small. If we go through this whole thing, and they use the proper significant figures and the proper precision and everything, we don't actually get a calculated value for x. So mathematically, it kind of fails us. Now, if we went to 7 or 8 decimal places and we, worked this out a little bit more exactly and we didn't round, then we might get a small answer. But you can ignore this part right here. You can ignore this because this value for x is so small that it's not really going to affect this number. So that's just to complete that. But if you have Ka values that are times 10 to the negative 3 and greater, then you do have to do this method where you have to use the quadratic formula. Okay? So that's just that special note that I wanted to make there. When the Ka values are 10 to the negative 4 or less, you do not have to use the minus x in the denominator like we just did in this last example.